Hello everyone, today we'll talk about advanced multi-objective and multimodal routing. In this course, we move beyond the fundamentals of GIS-based route optimization and focus on advanced routing concepts. While basic routing often aims to find the shortest or fastest path, real-world routing problems are usually more complex and involve multiple objectives, constraints, and operational requirements. Advanced routing matters because practical scenarios rarely rely on a single optimization criterion. Factors such as efficiency, accessibility, sustainability, and operational constraints must often be considered together. Advanced routing approaches enable these complex decision-making processes to be modeled and analyzed more effectively. This topic builds directly on the concepts introduced in Course 411. It extends basic routing parameters, network structures, and cost concepts, and applies them to more complex routing scenarios. By doing so, it prepares learners to understand advanced routing services and optimization strategies that will be explored throughout this topic and in the following case studies. Routing becomes advanced when it goes beyond calculating a single shortest or fastest path. In real-world scenarios, routing problems often involve multiple goals that must be considered simultaneously, rather than relying on a single optimization criterion. Advanced routing is characterized by the presence of multiple optimization objectives, various constraints, and more complex decision logic. These elements require routing systems to evaluate trade-offs and make decisions based on a combination of factors rather than a single metric. Basic routing approaches are often insufficient for practical applications because they oversimplify real-world conditions. Advanced routing methods allow routing systems to better reflect operational complexity and support more realistic and effective decision-making processes. Single objective routing focuses on optimizing a single cost parameter, such as travel time or travel distance. In this approach, the routing system evaluates all possible paths and selects the route that minimizes the chosen cost. While this method is effective for simple scenarios, it often fails to capture the complexity of real-world routing problems. Multi-objective routing, on the other hand, considers multiple optimization goals simultaneously. These goals may include minimizing time and distance, improving operational efficiency, or satisfying specific constraints. Instead of producing a single optimal solution based on one criterion, multi-objective routing evaluates trade-offs between different objectives. Multi-objective routing is needed because real-world routing scenarios rarely involve a single objective. By considering multiple factors together, advanced routing systems can generate more realistic, flexible, and context-aware routing decisions. Routing costs are measurable values used to evaluate and compare alternative routes. These costs represent what the routing system is trying to minimize or optimize during route calculation. Common routing costs include travel time, travel distance, and other operational measures related to efficiency. Optimization objectives define the goals of the routing process. Depending on the scenario, the objective may be to minimize travel time, reduce total distance traveled, or improve overall operational efficiency. Each objective reflects a different operational priority and influences how routing decisions are made. There is a direct relationship between routing costs and optimization objectives. The selected objective determines which costs are prioritized during route calculation. As a result, different objectives can lead to different routing outcomes, even when the same network and locations are used. A trade-off occurs when improving one optimization objective leads to a compromise in another. Trade-offs are a natural part of multi-objective routing problems and arise whenever multiple goals must be considered at the same time. One common example of a routing trade-off is the choice between the fastest route and the shortest route. A faster route may involve longer distance, while a shorter route may take more time due to road conditions or traffic. Similar trade-offs exist between operational efficiency and service coverage, or between speed and specific operational constraints. Trade-offs matter because there is rarely a single route that is optimal for all objectives. Routing decisions must be made based on priorities and the specific context of the problem. Advanced routing systems help evaluate these trade-offs and support more informed and balanced decision-making. Matrix calculations form the foundation of advanced routing and optimization problems. A routing matrix provides distance and travel time relationships between multiple locations, allowing routing systems to understand how each location is connected to others in terms of cost. In complex routing scenarios, such as those involving multiple destinations or operational constraints, matrix calculations are essential. They allow routing systems to evaluate alternative routes, compare different sequences of visits, and support more advanced decision-making processes. The matrix serves as a bridge between simple routing and complex optimization models. By providing structured cost information between locations, it enables advanced routing algorithms to operate efficiently and supports the transition from basic route calculations to large-scale optimization problems. Matrix and delta matrix calculations play a critical role in advanced routing scenarios. A standard matrix performs n-by-n calculations, where distances and travel times are computed between all points in a set. This approach is useful when all locations need to be evaluated against each other. Delta matrix calculations, on the other hand, support n-by-m scenarios, where the number of origin points and destination points does not need to be equal. This makes delta matrix especially suitable for advanced routing problems such as one-to-many or many-to-many analyses. Advanced use of matrix calculations is important because routing complexity increases rapidly as the number of locations grows. By selecting the appropriate matrix type, routing systems can improve computational performance, support scalable analysis, and enable more flexible and efficient routing solutions in large-scale operational environments. Route Basic is a routing service designed to calculate a route between a single origin and a single destination. It focuses on optimizing one objective at a time, typically selecting either the fastest route based on travel time or the shortest route based on distance. This service is well suited for simple routing scenarios where decision complexity is low and only one optimization goal is required. Examples include basic navigation tasks or straightforward point-to-point travel where additional constraints or objectives are minimal. However, Route Basic has limitations in advanced routing contexts. Because it optimizes only a single objective, it does not support trade-off analysis or complex decision-making involving multiple priorities. For this reason, Route Basic serves as a foundational routing service but is often insufficient for advanced operational and optimization scenarios. Route Advance is a routing service designed for scenarios where multiple locations must be visited in a predefined order. Unlike simple point-to-point routing, this service allows intermediate visit points to be included between the starting point and the final destination. A key characteristic of Route Advance is that the visiting sequence is fixed. The routing system does not optimize the order of visits but instead calculates the best route that follows the given sequence. This makes Route Advance suitable for use cases where visit order is determined by operational rules or external requirements. In the context of advanced routing, Route Advance serves as a transitional service. It extends basic routing by supporting multiple stops, while still operating within a constrained decision framework. More complex optimization problems, such as those that determine visit order automatically, are addressed by other routing approaches discussed in later topics. Routing with constraints and restrictions involves applying specific rules that limit where and how routes can be calculated. These restrictions are used to ensure that routing results comply with legal requirements, safety considerations, and operational policies. Common routing restrictions include roads or areas that are prohibited for certain vehicle types, time-based access limitations, and special regulations such as restrictions on hazardous material transportation. These constraints must be explicitly included in routing calculations to reflect real-world conditions. Incorporating restrictions has a significant impact on routing results. By excluding invalid or prohibited paths, routing systems generate safer, more realistic, and operationally feasible routes. This capability is especially important in advanced routing scenarios where compliance and reliability are critical. In advanced routing, Constraints can be classified as hard constraints and soft constraints. Hard constraints are mandatory rules that must always be respected during routing calculations. If a route violates a hard constraint, it is considered invalid and cannot be selected. Examples include prohibited roads, legal vehicle restrictions, or mandatory time windows. Soft constraints, on the other hand, represent preferred conditions rather than strict requirements. These may include avoiding congested roads, minimizing travel through certain areas, or favoring specific road types. Soft constraints can be relaxed when necessary to ensure that a feasible route is found. Understanding the difference between hard and soft constraints is essential in advanced routing. Hard constraints guarantee safety and legal compliance, while soft constraints provide flexibility and allow routing systems to balance optimization goals with real-world practicality. Multimodal routing refers to routing approaches that involve more than one mode of transportation within a single journey. Instead of relying on a single travel mode, multimodal routing combines different modes to reflect how movement occurs in real-world environments. Multimodal routing is needed because single-mode routing is often insufficient, especially in urban contexts. Many mobility and logistics scenarios require transitions between different transportation modes due to access restrictions, infrastructure limitations, or operational requirements. Common examples of multimodal routing include scenarios where a vehicle is used for part of a journey and pedestrian travel is required for the final segment, or where trucks must avoid restricted zones and switch to alternative modes for last-mile access. By supporting these combinations, multimodal routing enables more realistic and flexible routing solutions. Travel modes define how a single type of movement behaves within a routing system. Examples include car, truck, and pedestrian modes, each with its own routing rules, access permissions, and constraints. In traditional routing, a route is calculated using only one of these modes from start to finish. Multimodal routing goes a step further by combining multiple travel modes within a single routing scenario. Instead of selecting only one mode, the routing system allows transitions between different modes during a journey, such as switching from vehicle travel to pedestrian movement. The key difference lies in integration. Travel modes operate independently, while multimodal routing integrates multiple modes into a unified decision process. This integration enables routing systems to better represent real-world mobility patterns and supports more flexible and realistic routing solutions. Isochrone analysis goes beyond identifying areas that can be reached within a given time or distance. In advanced routing, isochrones function as decision support tools that help evaluate accessibility and spatial coverage. By generating reachable areas based on time or distance thresholds, isochrone analysis allows planners and decision-makers to assess how well locations are served under different routing scenarios. This makes isochrones especially valuable for service area analysis, facility planning, and accessibility studies. Isochrone analysis supports comparison between alternative scenarios, such as different service locations or routing strategies. By visualizing and quantifying accessibility, isochrones contribute to more informed planning and optimization decisions in advanced routing applications. Accessibility analysis focuses on how easily locations can be reached from a given point or set of points. In routing contexts, accessibility is typically measured using travel time, distance, or other travel-related conditions that affect movement. Coverage analysis builds on accessibility by identifying which areas are served within predefined thresholds, such as a maximum travel time or distance. This type of analysis helps reveal gaps in service coverage and highlights regions that may be underserved or difficult to reach. In advanced routing, accessibility and coverage analysis play an important role in service planning and optimization. These analyses support informed decisions in urban mobility, infrastructure development, and resource allocation by providing a clear understanding of how routing performance affects spatial access. Scalability is a critical consideration in advanced routing because routing complexity increases significantly as the number of locations grows. While simple routing problems can be solved quickly, advanced routing scenarios often involve large data sets, multiple destinations, and complex constraints. One of the main performance challenges in advanced routing is the rapid growth of matrix size. As the number of locations increases, the computational effort required to calculate distance and time relationships also increases. Real-time routing scenarios add further complexity by requiring fast and efficient computations. Managing scale in advanced routing requires careful selection of routing services and strategies. Using matrix and delta matrix calculations appropriately helps reduce computational load and supports efficient routing analysis. By considering scalability and performance, advanced routing systems can remain responsive and effective even in large-scale operational environments. Selecting the right routing service is a key step in advanced routing. Different routing problems have different requirements, and choosing an inappropriate service can lead to inefficient or inaccurate results. Effective service selection ensures that routing analysis aligns with the specific characteristics of the problem. Simple point-to-point routing scenarios are best handled using route basic, while scenarios involving multiple stops with a predefined order require route advance. Routing with restrictions is essential when legal, safety, or operational constraints must be respected. Isochrone analysis, on the other hand, is most suitable for evaluating accessibility and service coverage. By matching routing problems with the appropriate services, routing systems can avoid unnecessary complexity, improve performance, and produce more reliable results. Service selection is therefore a critical decision in advanced routing workflows. Advanced routing concepts are applied across a wide range of practical scenarios. In urban mobility, advanced routing supports the management of complex travel patterns and helps improve accessibility and overall efficiency within cities. In field operations, advanced routing is used to optimize routes while respecting operational constraints such as working hours, access limitations, and service priorities. This leads to better scheduling and more effective use of resources. In logistics and service delivery, advanced routing helps balance multiple objectives, such as minimizing time and distance while maximizing coverage. These applications demonstrate how advanced routing methods support sustainable, efficient, and real-world operational decision-making. In this course, we explored advanced routing concepts that extend beyond basic shortest or fastest route calculations. Advanced routing considers multiple objectives, constraints, and decision criteria to better reflect real-world routing challenges. Key components of advanced routing include matrix-based analysis, effective handling of constraints, and support for multi-modal routing and accessibility analysis. These elements enable routing systems to address complex operational and planning scenarios. By understanding these advanced concepts, learners gain the ability to interpret and apply advanced routing strategies. This knowledge prepares them to work with complex routing services and supports the practical application of routing solutions in real-world environments. This course provides the conceptual and technical foundation required for applying advanced routing in real-world contexts. The advanced routing principles discussed here form the basis for practical optimization and decision-making scenarios. In the next course, these concepts will be applied through case studies that demonstrate how advanced routing strategies are used in operational environments. This transition from theory to practice highlights the real-world value of advanced routing and prepares learners to engage with applied routing solutions.